So we're discussing about elevation of boiling point. Elevation of boiling point, right? So we all know that if you take a pure solvent, the vapor pressure of pure solvent is usually denoted, we denote vapor pressure as P naught. So P naught is the vapor pressure of pure solvent. Okay. In this, if we add a non-volatile solute, okay, if we add a non-volatile solute, we'll get a solution. The vapor pressure of the solution we represent normally with the symbol P. P means vapor pressure of solution. P naught is vapor pressure of pure solvent. When you add a non-volatile solute, the vapor pressure of the solution is less than the vapor pressure of pure solvent. Okay, this is the first point you should keep in mind. Always, whenever you add a non-volatile solute to a pure solvent, the vapor pressure of the solution will be less than the vapor pressure of pure solvent. Okay. You also know that boiling point, okay, depends on the vapor pressure. If vapor pressure is high, boiling point will be low. If vapor pressure is low, boiling point will be high. Okay. In the last class, I took water as an example. So you take water as solvent, okay, and we discussed the phase diagram of water. Right. So in the phase diagram of water, we plot pressure in y-axis and temperature in x-axis. Okay, and the graph will appear something like this. I'm just showing some schematic diagram. Okay. So this is the phase diagram of water. In this phase diagram, this region consists of solid water, that is ice. This region consists of liquid water, and this region consists of water vapor. Okay. And I'll take this point as O, and this curve, I'll represent this curve as OA. Students, keep this in mind. Along the curve OA, liquid water and water vapor are in equilibrium. The temperature at which liquid water and water vapor are in equilibrium is called boiling point. So along this line, you take any temperature, right? Whatever may be the temperature, okay, along this line, along this curve, all those temperatures indicate a boiling point. Okay, so this temperature represent a boiling point, this temperature represent a boiling point, right? So here this is the boiling point, but correspondingly the external pressure should change. Okay, that's the point, right? If external pressure is high, boiling point also high. If external pressure is low, correct? If external pressure is low, boiling point also low. Keep this in mind. If external pressure is high, boiling point is high. If external pressure is low, boiling point also low. That is why if you see normally the external pressure at sea level, okay, at sea level is actually 1 atmosphere. Therefore, at 1 atmosphere, water boils at, you know very well, boiling point of water is 100 degrees Celsius or 373 Kelvin, roughly, okay, we say. But if you go to some hill station, right, at the top of the hill station, the pressure will be, external pressure will be less than 1 atmosphere. Say for example, if it is 0.8 atmosphere, right, as the external pressure is low, boiling point also low. So in hill stations, okay, at the top of the hill station, at the top, the temperature will be the boiling point, right? Boiling point of same water will not be 373 Kelvin. It will be roughly less than that. So maybe 360 Kelvin, like that. Is it clear, students? This is very important. As external pressure changes, boiling point will change. Actually, as the external pressure increases, boiling point also increases. Right? This is for pure water. This is for pure water. Now, what I am going to do, I will take pure water, then I'll add a non-volatile solute, and we see what changes happens. Okay, so in the same phase diagram, I'll take the same phase diagram. Here we have pressure, here we have temperature. Okay, so these are the schematic diagram. Right, as I told you, here we have liquid water. Right, here we have ice, solid water, and let me put simply yes, solid. Here we have liquid, here we have vapor. Here we have solid water, liquid water, water vapor. Okay, this is for pure solvent. You know very well, students, you know, when you add a non-volatile solute, the vapor pressure of the solution will be less. Okay, so this is the boiling point curve. Students, observe carefully. As the external pressure increases, boiling point also increases, I have told you. Now, what is the normal boiling point? At 1 atmosphere pressure, okay, whatever right, is the temperature, or the temperature at which if the external pressure is 1 atmosphere, then the temperature at which liquid water and water vapor are in equilibrium, that temperature is called the normal boiling point. So this is boiling point of pure water. Let me represent as T0. I have taken water as an example. Water is used as solvent for many cases, so we have taken water. So this is normal boiling point of water. Normal boiling point means external pressure should be 1 atmosphere. That's all. Okay, so this is pure water. So let me call it as a solvent. So this is for pure solvent. This curve indicate for pure solvent. Pure solvent. Now, what happens if you add a non-volatile solute? Right? If you add non-volatile solute, then the vapor pressure of the solution will decrease. You know very well, right? Just now we discussed. When you add a non-volatile solute, whenever you add a non-volatile solute, vapor pressure of the solution will be less than the vapor pressure of your solvent. So, at any point, the vapor pressure, okay, of the solution will be less than this. Okay, let me draw a curve like this. So, this is for vapor pressure of solution. Why this curve is lower than this? Okay, because the pressure decreases. If you add a non-volatile solute, the pressure will decrease, right? And if see, this line will go like this. Now, what is the boiling point of solution? Okay, at 1 atmosphere pressure. The boiling point of solution is just extrapolate, just extend the straight line here, and this point is the normal boiling point of solution. Let me represent that as T. T is the normal boiling point of solution. T0 is the normal boiling point of pure solvent. Students, observe carefully. Observe carefully. I'll take only these two curves and I'll explain so that we can avoid the unwanted curves here. So pressure, temperature. I'll take only these two. So here we have a liquid pure solvent curve, and this is the curve for the solution. Okay, the above one is for pure solvent. This is for pure solvent, and this curve is for solution containing non-volatile solute. Why this curve is below? Why solution curve is below? Because if you add a non-volatile solute, vapor pressure decreases. Vapor pressure decreases. That's why this line is below the solvent line. Now you take some external pressure. Okay, at the sea level the external pressure is usually 1 atmosphere, right? So at 1 atmosphere pressure, what will be the boiling point of, okay, just draw a straight line, and this straight line cuts the solvent here and solution line here, and this temperature is the boiling point of pure solvent, and this temperature is the boiling point of solution. Okay, students, is this clear? And this is very important, this gap or this difference is what we call as delta TB, elevation in boiling point. So keep this in mind. Vapor pressure of solution is less than vapor pressure of pure solvent when we add a non-volatile solute. So that what happens, boiling point of solution become high, correct? Solution boiling point is high compared to, so solution boiling point is high compared to boiling point of pure solvent. Okay, and therefore the difference, what is the difference? Difference is high value minus lower value. Higher value is the boiling point of solution minus boiling point of pure solvent, and this is called the elevation in boiling point. Elevation of boiling point. Students, is this clear? Any doubt here? Is this clear, students?
Yes, sir.
Yeah. Now, suppose assume that I'll take some solvent, pure solvent, and I got some curve like this for various pressures, for various external pressure. The boiling point will appear like this, and I'll take some solution, okay, by adding some non-volatile solute. Students, suppose if I add some amount of solute, say 0.1 gram of solute. Students, observe carefully. I'll take 0.1 gram of solute and I'll add this solute in water. Okay, I'll get a solution. Say the molality of the solution is, say, for example, 0.1. I have added 0.1 gram of solute in solvent such that the molality of the solution is 0.1. For 0.1 molar solution, the delta TB, okay, you will get some value of delta TB. Suppose instead of 0.1, if I add 0.5 gram of solute, I am adding same solute, okay, and by adding 0.5 gram, suppose I am getting molality as, say, for example, 0.3, some molality. So what is happening? Before we added just 0.1 gram, so that molality is 0.1. I'm saying, just for understanding purpose, I'm saying, don't worry about how to get this 0.1 and all, okay. You take 0.1 gram of solute, add the solute in water, you will get a solution, and the molality of the solution is 0.1. For 0.1 solution, this is the solution vapor pressure curve we got, and this is the delta TB. You will get some value of delta TB while adding 0.1 gram of solute. Now what is I'm going to do? I'll take again pure water and I'll add 0.5 gram of solute, same solute. So that as let us consider molality of the solution is 0.3. So what happened here? What we did, we have increased the molality. Listen, if this is the solution curve for 0.1 gram of solute, if you add 0.5 gram, what will happen to the vapor pressure curve? If you add more and more solute, okay, vapor pressure will decrease. So this line, let me draw here. This line is another vapor pressure curve for solution, but here in the solution we have added 0.5 gram of solute. Okay, students, now observe carefully, and this is the boiling point of solution now, and this gap is the delta TB for this solution. Students, are you able to follow? This gap is the delta TB for 0.5 for solution containing 0.5 gram of solute, and this is the delta TB for solution containing 0.1 gram of solute. So what does this indicate? It indicates that elevation of boiling point depends on the amount of solute or molality of the solution. Okay, so let me write to the next page. So what does this indicate? So it is very clear that delta TB is directly proportional to molality of the solution. It's directly proportional to molality of the solution. Okay, it is directly proportional to molality of the solution, right? Or if I equate this, we should introduce a constant, and that constant is Kb into m. What is this Kb? This Kb is called Bilioscopic Constant. Let me write here. Kb is called Bilioscopic Constant. Bilioscopic Constant. You can also call this as molal boiling point elevation constant, right? It's also called molal boiling point elevation constant. Boiling point elevation constant. Okay, students, this is the usual representation, but depending upon your electrolyte your electrolyte may be a non-electrolyte. I'm very sorry. Your solute may be an electrolyte. Your solute may be a non-electrolyte. Okay. So depending upon whether the solute is electrolyte or non-electrolyte, the number of particles will change. I have told you colligative property is a property which depends on number of particles of the solute. Okay, so depending upon the solute that we add, we may add electrolyte or non-electrolyte, so the number of particles will change. Therefore, the very correct expression for colligative for delta TB is, let me write here, delta TB is equal to I into Kb into m. This is the perfect expression for delta TB, where this I is called Van 't Hoff factor. Last class I have told you, I is called Van 't Hoff factor. Okay, that will take care of whether you are adding electrolyte or non-electrolyte, right? And whatever number of particles we get, right? That will take care of this. So depending upon the number of particles, right, the delta TB will change. Therefore, this I must be included. Very, very important, right? And you know very well, last class I have told you, I is equal to 1 for non-electrolyte. For non-electrolyte, I have told you. So if I put I equal to 1, I will get this expression. So this expression is applicable for non-electrolyte. What is non-electrolyte? Very simple. See, you take some solvent. Now, if I add, say for example, if I add 1000 molecules of solute, and if I get only 1000 particles, okay, I am adding 1000 molecules. That is 1000 particles, right? Let us assume it as a particle. Okay, I am adding 1000 particles of solute. If I get same 1000 particle in water, we call those electrolyte as solute as non-electrolyte. For non-electrolyte, I is equal to 1. If I put I equal to 1, I will get the same expression. But this expression is not applicable for electrolyte. This is applicable only for non-electrolyte. That is why we are including this I. So if you include this I, you will get the full expression for delta TB. Delta TB equal to I into Kb into m. Kb is a Bilioscopic constant. Okay, take note. Kb is a Bilioscopic constant, and Kb is a constant for a given solvent. Okay, let me write. And before going to see the other informations, students observe carefully. For non-electrolyte, I is equal to 1. I have told you. For non-electrolyte, I equal to 1. If it is an electrolyte, last class also I have told you. If it is an electrolyte, then the electrolyte may undergo dissociation in solution. Some electrolyte may also undergo association. Some electrolyte may also undergo association. Okay. In the case of dissociation, suppose if your electrolyte is strong electrolyte, in this case, if your electrolyte is strong electrolyte, in this case, I should be equal to N. I should be equal to N. Okay, what is N? N is the number of particles produced from one molecule, or number of ions produced from one molecule. Okay, so what is N here? N is number of ions from one molecule. One molecule produce how many ions you find out. That is the value of N. So for strong electrolyte, I is equal to N. Okay, whereas for weak electrolyte, okay, I should be greater than 1, but we don't know what is the value that we can calculate. It should be greater than 1 in the case of dissociation. In the case of association, I value should be less than 1. Students, observe all these points, which are all very, very important. I repeat, in the case of non-electrolyte, I is equal to 1, no problem. If electrolyte undergo dissociation, then you see the electrolyte whether it is strong or weak. If the electrolyte is strong, then I is equal to number of ions produced from one molecule. Okay, if the electrolyte is weak, then I should be greater than 1, and that we have to calculate. We will discuss that how to calculate this value. If the electrolyte undergo dissociation, sometime electrolyte may also undergo association. If the electrolyte undergo association, I value will be less than 1. Okay, these are all called Vanta factors. We will discuss about this, okay, as we go along. Right now, remember this this expression delta TB is equal to I into KB into M, where KB is called a Bilioscopic constant and M is the molality of the solution, and delta TB is the elevation of boiling point. Okay, so it is very clear that elevation of boiling point depends on molality of the solution. If you add more solute, molality will increase, so elevation of boiling point also will increase. Okay, now, so this is the expression we had, that is delta TB equal to I into KB into M. Right, this is our equation. Now, I'll keep all these things as such, delta TB, I, KB as such. Okay, what is molality? You know very well, molality is nothing but number of moles of solute divided by mass of solvent. 2 represents solute, 1 represents solvent. Okay, number of moles of solute divided by mass of solvent in kilogram. It should be in kilogram, but usually we'll give this in gram. So divide this value by 1000. Okay, divide this value by 1000 so that it will become kilogram. Right now, let me rearrange this. So delta TB equal to I into KB into this 1000 will go to the numerator. So 1000 times N2 by W1. Here W1 is in grams. Okay. Now, we know very well number of moles is nothing but mass by molar mass. So if I include all the values, delta TB equal to I into Kb into 1000 into W2 by, I'll keep this W1 as such, W1 in gram and W2 also in gram, okay, and molar mass of solute M2. W2 by M2 will give you number of moles, okay. And what is the use of this expression? Students, observe carefully. If you know the value of I, Kb and weight of solute, weight of solvent, then you can determine what is called the molecular weight of the solute. M2 of the solute can be determined, okay, by measuring the elevation of boiling point. Okay, students, is this clear? Any doubt here? Any doubt?
No, sir.
Hello, students, are you able to follow this?
Yes, sir.
Yeah, right. Take down. So using this formula, you can calculate the molar mass of the solute. Okay, suppose if some unknown solute is given, right, you take some known solvent, add the unknown solute in the known solvent and prepare some solution having some molality. Okay, once you know this value of you measure delta Tb through experiment, and if you know the value of W2, W1, Kb, you can calculate the molar mass of the solute. Okay, how to calculate Kb? Students, for this we have a special derivation, but I'm not going to do that, which require the concept of chemical potential. You may not aware of that, so I'm not going to discuss that, but I'll give you the final expression. How to calculate the value of Kb? Kb is called Bilioscopic constant. Bilioscopic constant is a constant for a given solvent. Let me write. Kb is a constant for a given solvent. Kb is a constant for a given solvent. Okay, and how to calculate Kb? We have derivation for this, but I'm not going to do that. Gas constant R into T naught. T naught is the boiling point of pure solvent, or T naught square, into molar mass of the solvent divided by 1000 into enthalpy of vaporization. Take down. Students, note down this. This is the formula we use to calculate Kb. Kb is Bilioscopic constant, also called molar boiling point elevation constant. Molar boiling point elevation constant. Okay. Here R is actually gas constant, universal gas constant, and the value of R is 8.314 joule per Kelvin per mole, or you can use 0.0821 liter atmosphere per Kelvin per mole. Okay, or you can use 1.987 roughly 2 calorie per degree per mole. These are all the values of R in different units. These are all the value of R in different units. Take down. Is it clear, student? Any doubt here? Is this clear? Yeah.
Yes.
R is the universal gas constant, and the value of R I have given here. T naught. What is T naught? T naught is the I'm sorry, this is the way we write. No, we put naught in the denominator. Yeah, I'm sorry. Denominator T naught. T naught is the boiling point of pure solvent. Boiling point of pure solvent. pure solvent. M1 is the molar mass of solvent. What is M1? M1 is the molar mass of solvent. Molar mass of solvent. Okay, and delta H vape, it is called enthalpy of vaporization. It's called enthalpy of vaporization. What is meant by that? It is the amount of heat. It is the amount of heat required to convert 1 mole of liquid into vapor at the boiling point. I repeat, it is, what is enthalpy of vaporization? It is amount of heat required, to convert 1 mole of liquid into vapor at the boiling point. So at the boiling point, to convert 1 mole of liquid into vapor, how much heat is required? That is nothing but enthalpy of vaporization. Okay, so you take the enthalpy of vaporization here and put molar mass of solvent, okay, and boiling point of solvent. If you substitute all the values, you will get the value of Kb. Kb is called a Bilioscopic constant. Okay, I'll give some of the values for I'll give Bilioscopic constant values for some few solvents, just for your reference, and you at least try to remember the value for Bilioscopic constant for water and for few solvents. Okay, so Bilioscopic constant Kb. Okay, and what is the SI unit? SI unit is this, kilogram Kelvin per mole. Kilogram Kelvin per mole. This is the unit of Kb. So Kb value, and I'll take some solvent, right? What is the value of Kb for different solvent? So first I'll take water. For water, what's the value of Kb? The Kb value for water is 0.513. In some book they'll give 0.52 also, okay, but this is the exact value, right? Exact value. Then second, let me take chloroform, CHCl3 chloroform. For chloroform, the value is 3.85, and for carbon tetrachloride, the value is 5.02, carbon tetrachloride. For benzene, C6H6, for benzene solvent, the value of Kb is 2.6. Okay, so just remember the at least for water you should remember a Bilioscopic constant of water is 0.513. Okay, take note. Students, is this clear? Any doubt? And remember the unit of Kb. Kb unit is kilogram Kelvin per mole. Students, what is a Bilioscopic constant? What is a Bilioscopic constant?
Molar boiling point elevation constant.
See, very simple. See, delta Tb equal to Kb into m. Okay, for non-electrolyte, right? For non-electrolyte, right? Delta Tb equal to Kb into, suppose your solute is non-electrolyte, for non-electrolyte solute. Okay, delta Tb equal to Kb into m, we know. Okay, and you can write this expression Kb equal to, students, whenever you want, you need to find the proportionality constant. You know very well this is a proportionality constant, right? I have told you this in the beginning. See, delta Tb is directly proportional to m. If we equate or if you convert the proportionality into equal, we should introduce a constant. So this constant is called a Bilioscopic constant, but mathematically it is called proportionality constant. Okay, whenever you want to find proportionality constant, what you have to do, you keep the other terms as 1 to define Kb, to define or to find what is Kb, or to understand what is Kb. What you have to do, the terms that are remaining with the Kb, okay, you keep all the terms as 1. So here I have m, put m equal to 1. If I put m equal to 1, what will I get? I will get delta Tb equal to Kb. Okay, if m is equal to 1. What is meant by this? So Kb, a bilioscopic constant, is nothing but boiling point elevation or elevation of boiling point when we add or when we take 1 molal solution. That is why it is called molal elevation boiling point constant. Okay, so what is Kb? Kb is nothing but elevation of boiling point of 1 molal solution. Simple. So what is Kb? You can write like this. Kb is nothing but elevation of boiling point of 1 molal solution. So it is the elevation of boiling point of 1 molal solution, which is called as Kb. Okay, students, keep this in mind. If you take some amount of solute, add the solute in water or some solvent, if you get 1 molal solution, for that solution you calculate or you measure the elevation in boiling point. Okay, so that elevation in boiling point will give you what is the value of Kb. Okay, so you can determine Kb experimentally like this, right? And you can also calculate Kb using this formula. This I have told you already. Using this, this is theoretical method. Theoretically, you can calculate Kb using this formula, right? You can also determine experimentally by using this one. What you have to do, you just put you prepare 1 molal solution and find the elevation in boiling point. Okay, and the elevation in boiling point is nothing but Kb. So Kb is nothing but elevation of boiling point of 1 molal solution. If you add some amount of solute and if you get 1 molal solution, for that solution whatever elevation of boiling point that comes, which is nothing but a bilioscopic constant. Is it clear, student? Okay, yeah. Then so we have discussed some essential points of elevation of boiling point. Okay, now we'll start the next before that, this is another important information I like to give. Students, keep this in mind. Delta Tb, elevation in boiling point, is equal to I into Kb into m, right? This is the expression, okay? Delta Tb is equal to I into Kb into m. Okay? Observe this carefully. Suppose I'll give a few solutions. For example, I'll give 0.1 molal, okay, a solution, 0.1 molal solution of aqueous solution, right? 0.1 molal aqueous solution of say for example urea, and I'll prepare 0.1 molal aqueous solution of sodium chloride, and I'll prepare 0.1 molal aqueous solution of sodium sulfate Na2SO4, and I will prepare 0.1 molal aqueous solution of K4FeCN6. Students, observe this. A very important question, often expected in competitive examinations. Okay, all the solutions have same molality. See, molality is same. All are aqueous solution. Aqueous solution means solvent is water. Solvent is water here. I have told you all are aqueous solution. So Kb value is a constant because we are taking water. Molality, yes, all the solutions have same molality. So for all the solution, molality is 0.1, 0.1, 0.1. So that is not that is not different. Okay, all are having same molality. So now in this case delta TB is directly is equal to or is proportional to I only. Okay, so in this case delta TB, right, is directly proportional to I only, because molality is same for all the solution, Kb value also same because all are aqueous solution. So solvent is water. For water Kb value is a constant. Okay, so Kb is constant for all the, for Kb is same for all these solution because we are taking aqueous solution, and molality also same. Therefore delta TB depends only on I. Okay, students, observe this carefully. What is the value of I here? For urea is non-electrolyte, so I equal to 1. For sodium chloride, students, observe carefully. For sodium chloride, sodium sulfate, potassium ferrocyanate, all these are strong electrolytes. All these are strong electrolytes. And you know very well, for strong electrolyte I is equal to N, because all these electrolytes will undergo dissociation. Sodium chloride dissociate, sodium sulfate dissociate, potassium ferrocyanate dissociate. Okay, now what you have to do, I value is equal to number of ions produced from one molecule. From sodium chloride, how many ions will get? One molecule of sodium chloride will give how many ions?
2.
Be louder, students.
2, sir.
2. Therefore I value equal to 2. From sodium sulfate, how many ions will get?
3, sir.
3. Therefore I value equal 3. From potassium ferrocyanate, you will get 4 potassium ion and 1 ferrocyanide ion, so the value is 5. Correct? So listen, as I increases, see, I increases, delta TB increases. What is delta TB? Delta TB is nothing but T minus T naught. Students, observe carefully. Delta TB is T minus T naught. Okay, T minus T naught. So what does this expression gives? Listen, T naught is constant. T naught is the boiling point of pure solvent. It is a constant. This is constant. Okay, if delta TB increases, students, observe carefully. If delta TB, right, as I increases, see, as I increases, delta TB will increase. Right, I'll write here. Observe carefully. As I increases, delta TB increases. Okay, if I increases, delta TB increases. Listen, T minus T naught is delta TB, correct? T naught is constant. Students, observe carefully. T naught is constant. So if T increases, T minus T naught will increase. Am I right? Correct?
Yes, sir.
So if delta TB increases, it means T must increase. So T, right? So which indicates that T must increase. What is T here, student? What is T? What is T? What is T naught?
Temperature of pure solvent.
Yeah, T is the boiling point of solution. Okay, as I value increases, boiling point of solution will increase. So for just for understanding purpose, you can write like this: boiling point of solution is directly proportional to I. As I increases, boiling point of solution increases. So usually they'll give 4 or 5 electrolyte, and they'll ask you to find out which solution has highest boiling point. So among the 4, right, although the molalities of these solutions are same, as number of particles is more in this case, okay, boiling point is highest among the 4. Okay, among these 4, boiling point is highest for this solution because number of particles produced is more. Okay, because you know very well, as I increases, boiling point will increase. Keep this information in mind, very, very important. And this is specifically important for competitive examinations. Okay, then. Now, let me go to the next one called depression in freezing point. Next colligative property. Depression in freezing point. Depression in freezing point. Depression in freezing point. Yes. See, what is freezing point first of all? Let me write simply FPT. FPT means freezing point. What is freezing point? Freezing point is nothing but the temperature at which vapor pressure of a liquid or some solution, right? It may be solvent or liquid, right? So I will write simply liquid. Vapor pressure of liquid. Students, observe this carefully. This liquid may be solvent. The liquid may be solvent, or the liquid may be a solution, whatever it is. It may be solvent or solution. The temperature at which vapor pressure of a liquid becomes equal to vapor pressure of the corresponding solid take down. If the vapor pressure of the solid and the vapor pressure of the liquid, if they become equal, okay, then the temperature at which these two become equal is called the freezing point. Right? Freezing point is nothing but vapor pressure of liquid and vapor pressure of the solid, corresponding solid. If you take pure solvent, it is a pure solid of pure solvent. If you take a solution, it is a solid of solution. Okay. So you measure the vapor pressure of the liquid and vapor pressure of the solid. If these two become equal at one particular temperature, then that temperature is the freezing point. Okay. In the case of water, okay, I'll take the phase diagram of water. You know very well the phase diagram of water. Students, why I am taking water as example for many often, because water is used as solvent for many colligative property studies. That's why I am using water. Okay, but this is the same concept is applicable for other solvent also. Okay, so I'll plot pressure in y-axis and temperature in x-axis, and this is the phase diagram of water. It will appear like this. Okay, phase diagram of water. And here we have ice, solid water. Here we have liquid water. Here we have water vapor. Solid, liquid, vapor. Okay. Now, students, I'll take some external. External pressure, right? Or see, at the sea level, the external pressure is 1 atmosphere. 1 atmosphere. Okay. You draw a straight line. Okay. You draw a straight line. See here, solid vapor pressure and liquid vapor pressure are equal, correct? So this temperature is the freezing point of pure solvent. Let me write it as T naught. T naught is the freezing point of pure solvent. Okay, freezing point of pure solvent. Student, note down this, very important. This is the freezing point of pure solvent. Now I'll write the freezing point of solution. Listen, if you add a non-volatile solute, okay, this is for pure water. This is for pure water or pure solvent. Okay, suppose if you add a non-volatile solute, I will get a solution, and you know very well when you add a non-volatile solute, vapor pressure will decrease. Therefore, this diagram, let me draw here. This curve represent the phase diagram for the solution. Phase diagram for the solution. Okay, I have denoted that using dotted lines. So this is for solution containing non-volatile solute. Okay, now see here, for the same external pressure, 1 atmosphere pressure, the freezing point is here. The freezing point is here. Okay, so this is the freezing point of solution containing some non-volatile solute. Now if you see, temperature increases from left to right, so which freezing point is high? Is the freezing point of solvent or freezing point of solution? Which one is high?
Solutions.
Yeah, so freezing point of solution is low, freezing point of solvent is high, correct? When you move from left to right. Left to right, temperature increases, so T and T0, if you compare, T0 is higher value. So it is very clear from this is that boiling point of pure solvent and boiling point of solution, if you compare, this is freezing point, right? Freezing point of pure solvent is higher than the freezing point of solution, no doubt. Very, very important, student, no doubt. This is freezing point. Okay, see in the previous case, that is in the elevation of boiling point, I utilize the same symbol T and T0. So if you get any confusion, right, you can also use some notation like this. You can put F here. What is TF? This is T0 F. This is TF. What is T0 F? Freezing point of pure solvent, and this is freezing point of solution. Or if you can understand just T and T0, that's well and good. Okay, it's up to you. Right, students, observe this carefully. So freezing point of solvent is higher than freezing point of solution. But in the elevation of boiling point, student, observe carefully, but in delta TB, in elevation of boiling point of solution and boiling point of pure solvent, if we compare, okay, this is boiling point of pure solvent and this is boiling point of solution. If we compare, boiling point of solution is greater. Very important. Solution boiling point is greater than solvent boiling point. But if you come to freezing point of solvent is greater than the freezing point of solution. Okay, so this gives you the freezing point. Okay, freezing point means the temperature at which solid vapor and liquid vapor become equal, right? Or vapor pressure of the liquid and vapor pressure of the solid become equal. So at this point the vapor pressures are equal. So that temperature is called the freezing point. Okay, students, is this clear? Any doubt in this? Any doubt?
No, sir.
Yeah, good, very good. This is for depression in freezing point, and this difference, right, is what we call as delta TF. This is called delta TF. Delta TF is the difference in the freezing point of pure solvent and the freezing point of solution. So let me write in the next page. Write in the next page. So what is delta TF? Delta TF is equal to, okay, freezing point of pure solvent T0 F minus freezing point of solution TF. Okay, let me write like this. Note down. Because higher value minus lower value will give you the difference. So delta TF is nothing but T0 F minus TF. Students, remember, T0 F is the freezing point of pure solvent. TF is the freezing point of solution. And this difference is directly proportional to molality of the solution. It is directly proportional to molality of the solution as usual. Right? And if I equate this, we should introduce a constant, and that constant is nothing but Kf into M. Okay, Kf into M. And this Kf, right? And depending upon the electrolyte, your solute may be, as I told you before, your solute may be an electrolyte, or your solute may be a non-electrolyte. So Because of this, what will happen? Number of particles will change. We have to include that here. So in order to include that, I'll introduce this I here. I into Kf into m. This I will take care of whether the solute undergo dissociation or association, or the solute, okay, remains as non-electrolyte. Okay, so that will take care of the number of particles. Okay, and the remaining expressions we know, Kf into m. So what does this indicate? It indicates that as molality increases, as the molality of the solution increases, delta Tf will increase. As the molality of the solution increases, delta Tf will increase. Okay. Now, what is Kf here? This Kf is called cryoscopic constant. Cryoscopic constant. Kb is called Bilioscopic constant. Kf is called cryoscopic constant, and it is also called as molal freezing point depression constant. Molal freezing point depression constant. Depression constant. Okay, cryoscopic constant. It is usually called as cryoscopic constant. Kf is called cryoscopic constant, and it is also called as molal freezing point depression constant. Okay, take note. Is this clear, student? Any doubt? See, I have taken water as an example, but same idea is applicable for other solvent also. Okay, right. Next, delta Tf equal to I into Kf into m, where Kf is the cryoscopic constant and m is the molality of the solution. Okay, now as usual, and in the place of m I'll put, okay, before going to see that, Kf is the cryoscopic constant, and the unit of Kf is Kf unit kilogram Kelvin per mole. Okay, now I'll give Kf values for different solvents. Kf is a constant for a given solvent. Okay, Kf is a constant for a given solvent. Now I will give you some the Kf values for some solvent which are frequently used. Okay, take note. The values are for water. Okay, if you use water solvent, then the value of Kf is 1.86. 1.86. Students, note down. These are all very important. And for benzene C6H6, for benzene the value is 5.12. Okay, it is not necessary to remember the values, but the values are very important. At least you remember the value of water. That's what I'll suggest. I'll suggest students to remember the value of water at least. Okay, so for water, delta T, the Kf value is 1.86. For cyclohexane, the value is 20.2. Okay, take note. We also have other solvent. Here I have given only few. Right, take note. At least for water, you remember the value of Kf. Kf is called cryoscopic constant. Okay, how to determine Kf? How to determine the value of Kf? Yes, we have theoretical method, and we can determine through experiment also. So experimentally, as I told you before, delta Tf is equal to I into Kf into m, that we know. For non-electrolyte, suppose to determine Kf, we usually take non-electrolyte. Okay, suppose your solute, if the solute is non-electrolyte, okay, in this case I value equal to 1. So if I equal to 1, right, I'll get this expression, that is delta Tf equal to Kf into m. To define Kf, you should keep, because Kf is the proportionality constant, so to define proportionality constant, you should keep all other quantities as 1. All other quantities present along with Kf, okay, you should keep them as 1. So if you put m equal to 1, m equal to 1 means 1 molar solution. If you put m equal to 1, whatever delta Tf come, that is nothing but equal to Kf. Okay, so if I put m equal to 1, let me write the next page. If I put m is equal to 1, if m equal to 1, then I'll get delta Tf equal to Kf. So what is Kf? Kf is nothing but depression in freezing point of 1 molar solution. Simple. So what's the definition for Kf? Kf is our cryoscopic constant is defined as, Kf is defined as, cryoscopic constant is defined as the depression in freezing point. Delta Tf means depression in freezing point. Okay, so the depression in freezing point of 1 molar solution. Okay, we have taken 1 molar solution, right? 1 molar solution. So whatever depression of freezing point occurs for 1 molar solution, that is nothing but equal to Kf. This is the experimental method of finding Kf. Okay, you can, if you want to find Kf, what you have to do, you prepare 1 molar solution, and for the solution you find out what is the delta Tf. That delta Tf equal to Kf. You can also determine Kf theoretically. There is a derivation available, but I am not going to do that. I am going to give you only the final expression. The expression is this: Kf equal to R into T naught F whole square. T naught F means freezing point of pure solvent, okay, square, into M1 molar mass of solvent divided by 1000 into enthalpy of fusion or melting, right? Enthalpy of fusion. Take 2. You can calculate Kf value using this formula. Okay, so in this formula you see only we have only variables which depends on solvent alone. See, T naught is freezing point of pure solvent, M1 is molar mass of solvent, enthalpy of fusion is the amount of heat required to convert 1 mole of solvent from solid to liquid, to convert 1 mole of liquid from solid state to liquid state. Okay, that's nothing but enthalpy of fusion at the freezing point. Take note, enthalpy of fusion is nothing but amount of heat required to convert 1 mole of solid into liquid at the freezing point. Here we take pure solvent. For pure solvent, how much heat is required? Is this clear, student? Any doubt? Any doubt here? Hello, students, are you able to follow?
Yes, sir.
Okay, yeah. Now, students, this is very, very important. See, delta Tf is equal to I into Kf into m, right? Students, all of you turn on your camera. Hello, students, turn on your camera. Hello, yeah. So delta Tf equal to I into Kf into m. This we know. Kf is a constant for a given solvent. Suppose if I give 4 solutions, all are having same molality. Okay, if molality are same for various solutions and Kf is same, okay, then in this case Kf and M are same, therefore I can say delta Tf is directly proportional to I. Okay, if Kf and molality are same for different solutions. If Kf, I am not saying that Kf and M are equal, okay, Kf for various solutions are equal and molality for various solutions are equal, right, for are same for different solutions, okay. What is the meaning? I will discuss. Students, keep this in mind. Delta Tf is nothing but freezing point of pure solvent minus freezing point of solution. Okay, I'm sorry. Freezing point of pure solvent minus freezing point of solution. This is constant. Students, observe carefully. This is constant. This is constant. Okay. So if this value increase, then delta Tf will decrease. Am I right? Student, this is constant. So this minus this will give you delta Tf. Okay. If this value increases, then T naught F minus Tf become small, or that will decrease. Okay. So what I am trying to say is that, see, as Tf decreases, suppose as Tf decreases, Tf means freezing point of solution. Because freezing point of solvent is constant, okay, this one is constant, okay, don't worry about that. If freezing point of solution decreases, then this minus this will give you delta Tf, okay. If this become low, higher value minus lower value will give you higher value, okay. Therefore delta Tf will increase. If as Tf decreases, delta Tf increases, right. Then second point, as I increases, student, I am giving you the same information the other way. As I increases, delta Tf increases because they are directly proportional. As I increases, delta Tf increases. If delta Tf increase, freezing point of solution will decrease. Is it clear, student? Okay. So
Yes, sir.
just for understanding purpose, I will say like this: freezing point of solution is inversely proportional to I. There is no inverse relation like this. This is for understanding purpose. As I increases, freezing point of solution will decrease. Note down, student. In the previous case, that is for elevation of boiling point, right? For elevation of boiling point, I have told you that I value see, in the case of elevation of boiling point, I have told you boiling point of solution is directly proportional to I. If I increases, boiling point will increase. But what about freezing point? For freezing point, Tf is inversely proportional to I. So this type of relation doesn't exist. There is no direct relation, but for understanding purpose or for solving problem, this is very useful. As I increases, Tf will decrease. Say for example, I will give a few solutions. See, 0.1 molal aqueous, right? Aqueous solution of 0.1 molal urea, aqueous solution of 0.1 molal potassium chloride, aqueous solution of 0.1 molal sodium sulfate, aqueous solution of 0.1 molal, right, aluminum sulfate, Al2SO4 thrice. Which one among the four, which one has highest or lowest freezing point? Which one has lowest freezing point? Which solution has lowest? Yeah, as I increases, freezing point will decrease, okay. So for this, I value is 1 because it is a non-electrolyte. For KCl, you will get 2 ions, so I equal to 2. For sodium sulfate, I equal to 3. For aluminum sulfate, you will get 2 aluminum ion, 3 sulfate ions, I equal to 5. As I increases, see, when you move down, I increases. As I increases, the freezing point will decrease. So, among these 4, this solution has the lowest freezing point. This solution has the lowest freezing point. Why? Because it can produce more particle. Okay? If the solvent is same and molalities are same, right, then you can compare the freezing point of solution by finding the value of I. Is this clear, student? Any doubt in this?
No, sir.
Yeah, good. So, with this, we have completed the depression in freezing point. I stop here. We will continue the osmotic pressure in the next